So now, so this is the the plot, right? So rather this this is the line given by the to train the fitted model training. Line, so this is good. So we actually visualize that, right? Visualize here. So this is the dividing line that maximizes the margin between the two set of points. See, because you think actual SVM right? SVM right? So we can be sure that because SVM gave it to us, right? Shape support vector machine, the algorithm they can see, we can be confident that this is the largest margin you can have. Okay. So notice that a few of the training points just touch the margin. Of your case, few training points. See, your case, एउटा दुईटा point touch गरेछ यो marginले अनि यहाँ तल चाहिँ एउटा point यो चाहिँ अलिकति यो छोको छ तर एक्ज्याक्टली छैन हैन यहाँ बेसिकली तीनटा point छ 1 2 and 3 यो तीनटा points हुन्छ है so they are indicated यसमा okay so these points are the pivotal elements of this fit which are known as support vectors है अनि यस्तोलाई यसलाई चाहिँ हामी के भन्छ भन्दाखेरि these are support vectors. Yes, yeah, not this one, right? So 1, 2, 3. And these are support vectors. 1, 2, and 3. I know it's support vectors. Right? They were not support vector machines. Right? And give the algorithm its name. Right? In scikit-learn, the identity of these points are stored in exactly the points are kunkuno. And see, it's stored here. Right? Because I'm a model trained by second. So if I run this, see. We get 3 support vectors, understand? So I get 0.44, 3.11, right? So 0.44, and you see, 3.1, see, this one, right? Second one, 2.33, 3.43, right? 2.33, and if you see 2.33, yanera somewhere, 2.33, 3.43, right? 2.33, you want to see, this one right here, right? 2.33, understand? 3 point something, I know. It's 3.43. This is 2.06 to 1.96. Hey, 2.06 1.96 is your point. I know. So these are called support vectors. Hey, yes, a support vectors. Support vectors. How many support vectors? 1 second. Okay. This one the red कतिवटा
red दुईवटा छ yellow एउटा
yes that's right hey so those are called support vectors right that these are support vectors okay all right so okay so a key to this classifier success is that for the fit on only the position of it so so this is the key on the only the position of the support vectors matter okay and then any points further from the margin, which are on the correct side, do not modify the fit. See? If I go, so basically, these are pivotal. Right? Pivotal means very, very important. Any June points are the further away they are from the margin. Right? No, okay, so they're not going to change this line. Right? Anyway, of this say, yeah, order point, yaner idea, I'm returning data. अर्को यहाँ अर्को एउटा point हुन्थ्यो भने तपाईको यो लाइन अर्कै आउँछ किनभने तपाईको सपोर्ट भेक्टर चेन्ज भयो है तर तपाईको ट्रेनिङ डेटामा यता जतिसुकै आओस् न तपाईको लाइन त यही नै आउँछ एज लङ एज तपाईको सपोर्ट भेक्टर यही छ भने अरु जति यो फर्दर वे है फर्दर वे यता जतिसुकै पोइन्ट आओस् न तपाईको यो सपोर्ट भेक्टर चेन्ज हुँदैन मतलब यो लाइन चेन्ज हुँदैन है तपाईको डिस्क्रिमिनेटिभ लाइन छ त्यो चेन्ज हुँदैन है as long as your support vectors are intact छ है तपाई जस्तै अर्को एउटा पोइन्ट जस्तै है जस्तै यहाँनेर जस्तै ट्रेनिङ डेटामा यहाँनेर एउटा येलो लाइन भइदियो भने तपाईको सपोर्ट भेक्टर नै चेन्ज मतलब सपोर्ट भेक्टर अब यो नयाँ सपोर्ट भेक्टर आउँछ है यो दिस इज नो लnger द सपोर्ट भेक्टर अर्को सपोर्ट भेक्टर हुन्छ अनि तपाईको यो डिस्क्रिमिनेटिभ लाइन नै चेन्ज हुन्छ so that's why they're called the pivotal okay? They're very pivotal that's हैन so pivotal elements are right there okay so
sir यसमा ट्रेनिङ डाटामा चाहिँ नोइज छ भने चाहिँ रेडमा नै एउटा कुनै येलो छ भने रेड भित्र
Okay. Yeah. So this one, yeah, we'll take care of that situation. Yeah, that's a very good question. Just you study nicely, study now. So it's very close together. So this example now. So this one, the C one, C sunny. Margin like soften okay. Softening the margin one. So we'll actually take. We'll deal with that. We can deal with that anyway. But good question. Okay, so now let's see. Okay, so let's see. Okay, let me run this. Okay, over ESMA, so here's say you do a plot, so you have a 60 ESMA XB right? Number of points. So you support vector, you say ESMA train value, and you discriminative line and your margins survive, and then XB sort of random points. Could even point or you margin with a vitragas in Telegardi, some support vector, all support vector Thapiela, and the region is my original contour support vector adjustment. Very good. The Tinora support vectors, and right, you let's say your margin of your Naya data, man. 1 second. Okay. So Naya data, kiss on diary. So okay. You couldn't even eat that you bitter possible side. Just a second. Exactly. Okay, sorry about that. Okay, anyway, so okay, यसमा कुनै पनि यहाँ भित्र पसेको छैन भनेपछि तपाईको यता जतिसुकै पोइन्ट धेरै थपिएको छ but it didn't change the model. The model को यो जुन discriminative line चाहिँ change भएको छ it's exactly the same. Exactly the same. So okay, so like in the left panel we see that the model and support vectors with 60 training points. In the right we have double the number of training points, but the model has not changed. The 3 support vectors from left one are still the support vectors from the right. So it's still the same support vectors are but still they are the same. But original support vectors support vectors. So no matter points are change. Okay, so okay, so this insensitivity to the exact behavior of distinct points is one of the strengths. This is the strength of SPM model. Okay, so if you're running this notebook, you're saying I can skip that part, right? Okay, so it's the same visualize. I mean, it doesn't run quite well here. So okay, maybe let's try it, see if it works. Okay. 10 minus the bio, so let's try 200 points. See, okay, let's say my 10 minus. See, it changes. It changes. Number points are bitra chire. Naya support. Say 1 is my case. Inner support vector. See, around 1.9 र 1. यो भने यो याद गर्नु होला यसैमा हामीले 200 वटा बनायो भने नाउ के भयो भन्दाखेरि अब अरु नयाँ पोइन्ट्सहरु यता यो भित्र छिर्यो नि हैन त्यसले गर्दाखेरि अब नयाँ सपोर्ट भेक्टर्सहरु आए 1 2 3 है नयाँ सपोर्ट भेक्टर्सहरु आए भने यो केसमा चेन्ज भयो किन भन्दाखेरि त्यो डिस्टेन्ट पोइन्ट्सहरु छ भने चाहिँ त्यो यदि अब हाम्रो यसमा चाहिँ हैन सबै जुन नयाँ पोइन्ट्सहरु थियो सबै यतातिर है यो लाइनमा अथवा यतातिर यो लाइनमा अथवा यतातिर हुन्थ्यो भने चाहिँ हाम्रो यो के पनि चेन्ज हुँदैन थियो है ओके अलराइट okay so next thing we're going to talk about is the kernel SPM right kernel SPM okay SPM becomes extremely okay so as kernel we saw the power of kernels basis function basis function so SPM becomes extremely powerful when it is combined with kernels. We have seen a version of kernels before in the basis function regressions. We projected our data into higher dimensional space, orco basis, and defined by polynomials and Gaussian basis functions, and we're able to fill nonlinear relationship with linear classifier. Okay, so let's see a similar thing here. Okay. So, okay, we have this. Our data is the same thing. Our data is radial, right? Radial data. It's a highly nonlinear. It's a linear, nonlinear data, right? And then over ISMA, we're trying to fit what? SPM, regular SPM, right? Okay, your discriminating line you your margin bar. Margin, right? So is it going to work? No way. Hey, you have to become it. It's my key trick long for you. And what do you think? It's my key idea. It's like we can still use support vector machine use gonna suck in. Right? For a cost. Key is gonna
circular decision boundary.
Okay, yes, sorry. Circle.
Dimensionality reduction.
Dimensional reduction ले खासै काम गर्दैन होला. Okay. Yes, dimensional reduction गर्दा we want to use support vector machine use गर्नु छ के. है support vector machine use गर्नु पर्छ.
Circle decision boundary गरेर गर्नु छ.
Yeah, yeah, that's right. Hey. So circular just circular type को हैन. Yeah, very good. So त्यसमा हामी के गर्न सक्छौँ भने यो we do जुन kernel, so we use some kind of kernel, like basis function use गर्नु पर्यो हैन. हामीले के गर्यो भन्दाखेरि basis function गरेर त्यो इनपुट लाई नै ट्रान्सफर्म गरेर हैन अर्को बेसिसमा लगाएर अनि त्यहाँ चाहिँ हामीले के गर्नु पर्यो SPM फिट गर्नु पर्यो है. एक्ज्याक्टली हामी जुन लिनियर रिग्रेसनमा गरेका थियौँ नि है, लिनियर रिग्रेसनमा के गर्यौँ भन्दाखेरि नन-लिनियर डेटालाई हामीले अर्को बेसिसमा लगेर हैन त्यहाँ चाहिँ हामीले लिनियर मोडल फिट गरेर फेरि ब्याक आएको थियौँ. त्यो गर्दाखेरि त्यो लिनियर मोडल ठ्याक्कै फिट भएको थियो हैन नन-लिनियर. त्यस्तै पनि यो नन-लिनियर डेटालाई हामीले हायर डिमेन्सनल हैन अर्को बेसिसमा लैजानु पर्यो है. सो some kind of basis function युज गर्नुपर्छ जसले कि यो डेटालाई अर्को बेसिसमा लैजान्छ, अर्को कोअर्डिनेट सिस्टममा लैजान्छ. अनि त्यहाँ चाहिँ हामीले चाहिँ के गर्न सकिन्छ भन्दाखेरि we can apply this regular SPM अनि यता आएर हाम्रो यो बेसिसमा आएर हामीले त्यसलाई प्लट गर्ने भने नाइसली त्यो सर्कुलर बाउन्ड्री आउँछ है, सर्कुलर टाइपको बाउन्ड्री है, क्लोज बाउन्ड्री. ओके, सो त्यसरी आउँछ है. सो विल सी द्याट है, विल सी द्याट. अब चाहिँ के गर्ने भन्दाखेरि there's no clear okay यो भयो अब यसमा हामी चाहिँ के गर्नु भन्दाखेरि there's something यो चाहिँ रेडियल बेसिस फंक्सन है. मैले बेसिस फंक्सन कुरा गरेँ नि. सो अब ल तपाईहरु याद गर्नुस् त व्हाट इज द बेसिस फंक्सन डु. बेसिस फंक्सनले के गरेको थियो लास्ट टाइम याद छ तपाईहरुलाई. बेसिस फंक्सनले के गर्छ जस्तै हामीले पोलिनोमियल पोलिनोमियल लगाएको थियो अनि पोलिनोमियल बेसिस फंक्सन लगाएको थियो है. ओके, त्यस्तै गाउसियन बेसिस भयो हैन. सो
नन-लिनियर
ओके बेसिस फंक्सनले के गर्छ भन्दाखेरि इनपुटलाई हैन इट टेक्स इनपुट एन्ड टेक्स इट टु अर्को डिमेन्सन है, अर्को बेसिसमा लैजान्छ नि त. त्यो फंक्सनले त्यो इनपुटलाई ट्रान्सफर्मेसन गरेर हैन इनपुटलाई त्यो बेसिस फंक्सनले के गर्छ भन्दाखेरि it takes the input and the input like अर्को बेसिसमा अर्को कोअर्डिनेट सिस्टममा अर्को हायर डिमेन्सनमा मोर कम्प्लेक्स स्पेसमा लैजान्छ हैन. ओके, सो we define that function जुन कि हामी त्यसलाई चाहिँ हामी रेडियल बेसिस फंक्सन है. सो यो चाहिँ we create this function है. सो के गर्छौं भन्दाखेरि सो रेडियल बेसिस फंक्सन है so हामीले यसरी we create this है radial basis function है okay अनि के गर्छौं भन्दाखेरि radial basis function and this is we can visualize this extra dimension using a three-dimensional plot if you're running okay so त्यो गरिसकेपछि हामीले के गर्छौं भन्दाखेरि अब यसलाई plot गरौँ है so sorry I didn't run this right I ran that and let's plot it hey okay अब यसमा one second let me admit okay so यसमा exactly अब यो 3D plot आएको छैन है न त 3D मा हामीले मजाले यसको घुमाएर हेर्नु हुन्थ्यो है अब यो 3D plot ठ्याक्क यस्तो हैन यसले सपोर्ट गरेको छैन यहाँ त हैन 3D सपोर्ट गरेको छैन so त्यसमा हामीले we could actually see है जस्तै 90 मा हेरौँ so okay so यसमा ठ्याक्कै सपोर्ट गरिरहेको छैन है so okay we can get rid of that है rather we can say okay right here so we can see that this additional dimension data becomes trivially linear separable by drawing a separate plane the separate plane r equals 0.7 right so let's see okay c equal to the 1 2 3 10 to the power 6 हैन अनि हामीले चाहिँ के भन्छ कर्नलमा rvf दियो okay radial basis function दियो है यो चाहिँ हामीले यो चाहिँ हामीले म्यानुअली गरेको चाहिँ यो radial basis function लाई सिमुलेट गरे मात्रै है सिमुलेसन गरेर अब यहाँ यो सिमुलेसन रन गर्नु हुन्थ्यो तर मेरो ग्राफिक्सले चाहिँ दिएन है okay anyway so here's the thing है के भने we create the classifier है बेसिकली हामी के गर्छौं भन्दाखेरि svc है अनि हामीले के गर्छौं त्यसलाई इन्स्टान्सिएट गर्दाखेरि कर्नलमा हामी rvf लिन्छौं rvf भनेको रेडियल बेसिस फंक्सन है रेडियल बेसिस फंक्सन हो यसमा अनि हामी हाई सी लिइरा छौं अनि यसलाई फिट गर्छौं है यसलाई फिट गर्छौं क्लासिफायरलाई फिट गर्यो अब फिट गरेर अब यसलाई लेट्स सी प्रेडिक्सन गरौँ है सी नाइस हैन सी अनि सर्कुलर डिस्टेन्स बाउन्ड्री अनि कसले भन्नुभयो सर्कुलर डिस्टेन्स बाउन्ड्री भनेर
सर म निरज
ओके भेरी गुड है मैले निरजले भन्नुभएको थियो नि हैन सो सर्कुलर सी अब यो के अब सी स्टिल यो एसपीएम हो कि हैन दिस इज एसपीएम है तर यसो माथि लिनियर थियो नि do you remember तपाईहरु हेर्नुस् त यहाँ हामीले कर्नलमा लिनियर लेखेको छौं है यहाँ कहाँनिर छ भन्दाखेरि यहाँनिर है सो हामीले कर्नल लिनियर लेखेको छ हेर्नुस् त कर्नल लिनियर है लिनियर कर्नल थियो है लिनियर कर्नल सो त्यसले गर्दाखेरि यहाँ हाम्रो लिनियर नै आयो हैन जब हामीले कर्नलमा हामीले के गर्यौं भन्दाखेरि हामीले कर्नलमा हामीले rvf है रेडियल बेसिस फंक्सन है रेडियल बेसिस फंक्सन गर्दाखेरि नाउ नाइसली हाम्रो के भयो भन्दाखेरि अब त्यो रेडियल बेसिस फंक्सनले के गर्यो भन्दाखेरि हाम्रो इनपुटलाई अर्को डाइमेन्सन अर्को कोअर्डिनेट सिस्टम नेभि रेडियल कोअर्डिनेट सिस्टम है सो त्यो कोअर्डिनेट सिस्टममा लगाएर त्यहाँ चाहिँ के गर्यो भन्दाखेरि रेगुलर एसपीएम हैन फिट गरिदियो हैन जहाँ कि इट फिट इज नाइसली देयर हैन अनि वी कम ब्याक टु दिस बेसिस अब यो बेसिसमा हुँदाखेरि वी क्यान सी नाइसली हैन it gives you this right which is kind of like magic okay so using this kernelized supports vector machine we learn a suitable nonlinear decision boundary right this is nonlinear this kernel transformation strategy is often used in machine learning to turn fast linear models into fast nonlinear models okay especially for models in which the kernel trick can be used right so very powerful yet so simple right so simple है कोड हेर्नुस् त कति हैन सो सिम्पली यसले के गरेछ हैन अर्को बेसिसमा लाएर सो कर्नल भनेको त्यही नै कर्नल भनेको बेसिस फंक्शन्स है बेसिस फंक्शन्स which take the input and take it to some other other basis okay so which is very powerful okay all right so अब अघिको somebody has was asking about जब त्यो त्यस्तो clearly separable हुँदैन हाम्रो डेटा त्यति बेला के गर्ने त भन्दाखेरि we can do something called softening the margins right tuning the SPM right softening the margins margin line it's a hard boundary for that right so our discussions thus far has been centered around very clean data sets in which a perfect decision boundary exists but what if your data has some amount of overlap right for example you may have data like this see right here so you call it सोध्नुभयो you सोध्नु भएको थियो नि यो क्वेशन
म निरजले सोधे
okay very good okay so this is what you are talking about right यस्तो केसमा के गर्ने Okay, exactly. You know? So I would say, let's see what you can do. So to handle this case, the SPM implementation has a lot of fudge factor. Fudge means fudge, you know fudgy, right? Fudgy means there's a clear-cut boundary now, okay? Right? The fuzzed lines, right? Exactly नेपालीमा के भन्छ, I'm not आएन word ठ्याक्कै, right? Which softens the margin. Right? That is, it allows some of the points to creep into the margin if that allows a better fit. The hardness of the margin is controlled by the tuning parameter C. Right? Again, हामीले C एकदमै ठुलो राखेको थियौँ, याद छ? 10 to the power 10, 10 to the power 6. Right? There's a hard boundary. You don't want to let the data go into the boundary. Right? Okay. So for very large C, the margin is hard. The points cannot lie in it, inside it, inside it. Right? The margin भित्र छिराउँदैन उसले. Right? For a smaller C, right? So like a C value is small, the margin is softer and can grow to encompass some points. Right? Margin is soft. Okay. So let's look at this. Say base matters. Now, so now I'm going to C is a very small one. C it ranges from 10 to 0.1. Right? Say C10, C equal to 10. It's not letting, so still 10 is equal to 10 to the power 6, 10 to the power 10, that's super ठुलो भयो. Just the say 10 गर्दाखेरि के भयो, look at this. Right? 10 मा के छ भन्दाखेरि so अलिअलि भित्र पसेको जस्तो छ, एक्ज्याक्टली भित्र पसेको छैन कुनै पनि डेटा. तर यसमा के भयो तपाईको 0.1 C एकदमै कम गर्दाखेरि चाहिँ now you're letting this go in. So you're letting these points in. Okay. So the optimal value of C parameter will depend on your data set and should be tuned using cross-validation or similar procedure. Right there. Okay. All right. So this is how you do it. C parameter then you can fit those data which are not cleanly separable. Right? Cleanly separable data. Okay. All right. So let's see. Next, quickly, let's do this face recognition. Right? Face recognition. Okay, so as an example of support vector machines in action, let's take a look at facial recognition problem. I will use the label faces in the wild data set. Right? So let's see. Let me take a quick break. About 1 minute, or 2 minutes. Okay. Okay, all right. So face recognition, hey. So it's still running. Okay, so it looks like it's a big data set, hey. So as an example of support vector machine in action, let's take a look at the facial recognition problem. We use the label faces in a wild data set, a wild data set, right? This were label faces, which consists of several thousand collated photos of various public figures. Right? A fetcher for the data is built in size to scikit-learn. Right? So it's taking a while. So let's do this. Let me interrupt the kernel. Interrupt it and let me run again. Right? Let's see. Okay, good. There's another problem. What is it? Let's see. File ended for end of stream. Okay, let's try again. Okay, yeah, very good. Right? So it's the Ariel Sharon, Colin Powell, who died a couple of weeks ago, right? Secretary of State, George Bush, right? Donald Rumsfeld, right? Secretary of Defense, George W. Bush. So these were the people when they were in power when I was in the US. Right? Okay, anyway, so all right, so let's plot these faces. Right? Okay. Okay, see, obviously your data set is the Calvin data set. Okay, you have this different, very well-known faces, of course. Okay. All right, each image consists of 62 by 47 pixels, nearly 3,000 pixels, say 62 by 47. You multiply somewhere near 3,000 pixels. Flat 3,000 pixels now, say. So we could proceed by simply using each pixel value as a feature. यो त हामीले पहिले पनि हेरे हो नि, जस्तै हाम्रो 8 by 8 कोमा हैन, हरेक पिक्सल इज अ फिचर है। यो सेम यसमा चाहिँ कति डिमेन्सनल भयो हाम्रो डेटा यहाँ। Each picture is how many dimensions? Flat गर्दाखेरि around
62 into 47.
47. That's right. Hey, 60 times 10. So almost 3,000. We don't know the exact number, so calculating on for. So, but let's say around 3,000. Hey, 3,000. So each whenever see hamro harek data चाहिँ कति भयो भन्दाखेरि around 3,000 dimensional. 3,000 dimensional. Right? Okay. Right. I'm a feature saying 3,000 dimensional. Right? So, so it is often, it is more effective to use some sort of preprocessor to extract more meaningful features. Okay, so yes, ma'am, we'll use some kind of principal component analysis. You want that covered in the mechanism. So it's what I'm giving. We bring it down 3,000 by 150 million. I'm doing the data use guys. Okay, dimensional reduction. Okay, let's see. What's the problem? Randomized PCA. Okay, randomized PCA. All right, it's my randomized PCA. Your library update way down. So rather, it's my about let's just use regular PCA. That let's see if that works. PCA, randomized PCA. Yeah, kind of randomized PC. And yeah, let's use regular PCA. Regular PCA. Okay, so looks like ran. Right? So let's see about, of course, we do PCS and PCA. We are so 3,000 dimensions or 150 million, right? And you white and equal to true you so these are some hyperparameters. And this was SVC, right? SVC, I'm the SVC बनाएको PCA भयो and SVC भयो and हाम्रो pipeline मा राख्यौं हाम्रो data goes through PCA, dimension reduce हुन्छ अनि the reduced dimension चाहिँ SVC मा जान्छ है। यो चाहिँ तपाईले बुझ्नु भएको छ of course है, किनभने we have already covered pipeline है। अब यो गरेर let's see, we have train test split गर्नु पर्यो। Let's see what's cross validation. Okay, scalar you could say package much or your train test split, right? Okay, so let's just try this one time, right? Oh, wait, first let me take your snip, right? The snip of this before I forget. Right? Oh, okay, let's do this. So here we go. Let me save it. Okay. Save. Okay. All right, very good. So sklearn import. So you orco package, you just change that answer. So you I'll have to Google, right? Let's see. No module name. Okay. Let's see. Okay, from import trainers from sklearn dot cross underscore validation, right?
सर मोडल सिलेक्सन हो कि जस्तो छ
Model selection. Okay, let's see. Linear regression. Okay, looks like here's the answer. Model there. Okay, now it's in the model selection. Yeah, thank you. Okay, yeah, model selection, Risa. Thank you. You change it around again. That version of model selection. So yeah, that should work. Yeah, very good. Of त्यो गरेर now हामी के गर्छौं ट्रेन स्प्लिट गर्यौं त्यसपछि we train on the X train Y train मा train गर्छौं है. So again I'm from my normal sklearn grid search. Grid search छैन. So यसमा पनि अब के चेन्ज भएको छ let's see. See. यदि चेन्ज गरिरहन्छ. Okay. Error. Okay. मैले अस्ति यो scikit-learn update गरेको थिएँ अनि okay, so let's see. Okay, answer to do with this, right? Model selection, right? Okay, so from here, okay, it's going to be model selection. Model selection, right? Okay, let's see. All right, so right, so model selection is my grid search CV. Grid search CV that we have already covered, right? Cross validation, right? Grid search, right? Grid search, combination of source sources. So I'm case 1, 5, 10, 50. C Sammy 1, 5, 10, 50. Gamma chain. You choose it as well. So it's going to take some time. Right? Take some time. And let's see. ग्रिड सर्च किन यसले त हरेक कम्बिनेसनमा ट्राई गर्नु पर्यो नि त हैन त्यो माथि हाम्रो के छ हाम्रो यस ग्रिड सर्च अब there's a lot of computation to do हैन त्यसले गर्दा अब यो चाहिँ अब मेरो जीपीयू छैन जीपीयू भएर छिटो हुन्थ्यो हैन कोलाबमा जीपीयू युज गर्न मिल्छ हैन अनि जीपीयू गरे भने इट्स मच फास्टर यो चाहिँ मेरो त खास सीपीयू छ मेरो पीसीमा चाहिँ आई डोन्ट हैव जीपीयू हैन जीपीयू भएको भए यो कुरा कोलाबमा चाहिँ जीपीयूमा भएर अलि फास्ट हुन्छ है किनभने त्यो हामीले जीपीयू युज गर्न पाउँछ नि त हैन ओके सो त्यो यो मेरो सीपीयू ले गर्दा अलिक टाइम लाग्छ है okay so anyway so if you run this then this is available to you please run that hey run garera and you can see how nicely it it works okay so okay so as ethnic right as ethnic we didn't have like cpu but then time like okay okay so that's it for today right so and then we'll meet tomorrow right that's Kivara Wednesday okay so we'll meet tomorrow okay bye bye have a good night